Today we're going to talk about the forces of rolling. This is section 11-4 in your textbook, so I think we have spread out textbooks around the room so that every desk or pair of desks has a book to share. All right, here we go. I've got a round disc, just like you see in the diagram in section 11-4, which I think is page 279, yeah, right there. If I put this, now I hope my table is level. It might not be level. My table, that's a good lesson right there. If I put this disc on the table and it starts to roll, right away you say to yourself, oh, my table's not level, right? If I put it, okay, it's level enough. Stop. There we go. It's close to being level. It sits there, it doesn't roll. If I put it on the ramp, it rolls.
What?
Amazing. Thank you for coming. That's today's lesson. No. What's the difference? Let's look at it from a physics viewpoint. Here's a diagram of the disc on the ramp. And if I asked you to say in one word, if you could describe in one word, why does that disc roll down the ramp, what would you say?
Gravity.
Gravity, sure, right? So how does gravity do it? Well, if we treat all the mass of the disk as if it's at its center of mass, which is what the definition of center of mass is, right? Pretend all the mass is at that point. Where's the point of support for the disk? Well, it's where the disk touches the ramp. Okay. So here's a diagram of the level surface, and there's two forces acting on the disk. Gravity, which we call the weight, mg, and the support force of the table, the normal force, which we know they're equal and opposite. They cancel each other out. The net force on the disk is zero. It doesn't accelerate. It's at rest. If you notice, if at the center of mass, both of those forces pass through the center of mass. Remember torque? If the force passes through the axis of rotation, no torque is produced. So that's exactly what's happening here. Both of those forces pass through the axis of rotation, and it doesn't rotate. But if we put it on the incline, now the weight is always straight down, right? But the point of support is here. So the normal force points like that, the gravitational force points like that. They're not in opposite directions anymore. There's no way those two vectors can add to zero. There must be a net force. And that is the, if I resolve, remember when we have an incline, we tip our axis so that the incline is the x-axis and perpendicular to that is the y-axis. Now my weight is no longer on the y-axis. The normal force is on the y-axis, but the weight is not, so I can resolve it into its x and y components, and I see that the y component is what cancels out with the normal force, and in the y direction there's no net force, there's no acceleration in the y direction, but this x component of weight now is the force that pushes or pulls, depending on how you look at it, pulls the disc down the ramp, and it moves. If there was no friction, though, you see here Fs, we'll talk about that in a minute. If there was no friction, what would happen to the disc? Would it still go down the ramp? Absolutely. What is different about the situation with friction than if there was no friction? It wouldn't roll, right? It would only slide down the ramp. In fact, I have a very rare, very expensive, hard to find, frictionless ball. Would you like to see it? I have to put it behind the curtain. You ready? It's going to only slide down the ramp and not roll.
Whoa, that's so weird.
What's going on?
There's a thingy inside.
It looks like it's sliding down the ramp, doesn't it? But there is a weighted ball inside surrounded by a clear plastic shell. And there's a liquid, I think it's water, that it's floating in. And so the ball always stays, there's a red dot on the top, you probably can't see it. The red dot always stays at the top because on the bottom there's like a weight inside. So it stays, but the shell is rolling. Anyway, It's a cool illusion. So that's what would happen if there was no friction. But there is friction. So what is making the thing rotate? We need a torque, don't we? If something is to rotate, we need a torque, which we know is a force applied at some distance away from the axis of rotation with a component, at least a component, that is perpendicular to the radius, right? So can you see if we say it's rotating about the center of mass, then Fs, the frictional force, is my force applied at this radial distance r, and that produces a torque, which causes it to rotate. If I were to push the wheel up the ramp, it would slide up the ramp. So if it's sliding up the ramp, friction always opposes motion. Which way is the friction? Down the ramp, right? And if I let it go down the ramp, it would slide down the ramp, so the friction acts up the ramp, okay? So you see, if we just let the wheel, if we push the wheel up the ramp, the frictional force is going to be in the down the ramp direction. And if we roll it down the ramp, then the frictional force is up the ramp in the direction. Kind of a cool thing to think about.
You have to be careful because the situation is different if the wheel just rolls up the ramp or if I push it up the ramp. So let's look at both of them. Here we see rolling up the ramp. So if the wheel is just rolling along across the floor to the right, and then it encounters this ramp and begins to roll up the ramp, we know the wheel is rolling in a clockwise direction. And if it weren't for friction right here, this wheel would slip. And the bottom of the wheel, since it's moving in a clockwise direction, would be moving to the left, so the frictional force would be to the right. And if it was slipping, this would be kinetic friction. If it's not slipping, it's static friction. But the way to tell, the best way to tell, is to look at the acceleration of the wheel, the angular acceleration of the wheel. If the angular velocity is decreasing, that means the angular acceleration is in a counterclockwise direction. And that means the frictional force must produce a torque that is counterclockwise. Remember, acceleration and torque are always going to be in the same direction. So the frictional force just rolling up the ramp is going to be up the ramp. If, however, the wheel was initially at rest and I started to push it up the ramp, then this surface right here would slide up the ramp, and that means the frictional force would be down the ramp, and the torque produced by a down the ramp frictional force would create a clockwise torque and increase the angular velocity in the clockwise direction as it moves from rest to rolling up the ramp. So just be careful. My suggestion is to look at the angular acceleration, and from that you know the net torque must be in that direction.
Another one, what if you got on your bicycle and you started to pedal the pedals? So let's say your friend is there and they lift the back tire of your bike off the ground while you're on it, or an exercise bike, for example, right? You start to pedal, the wheel starts to move, our bike is facing this way, the wheel starts to move this way. If it was in touch with the ground, it would slide to the rear. So if the wheel is sliding to the rear, which way does the friction act? Opposite that, forward. And that's the force that causes your bike to move forward. So while you're pedaling and accelerating your bike, the frictional force on the back tire is forward. But now think about the front tire. Here's the fork, right? The fork of your bike. If there was no friction and your bike started to move forward, the front tire would slide across the ground in the forward direction. So which way is the frictional force? In the backward direction. So the rear frictional force causes your front tire to spin that way. But isn't your back tire also spinning in the same direction? But we just said the frictional force on the back tire is forward. So what's going on there?
Science.
Well, don't forget our equation for alpha is angular acceleration. If the velocity of the angular velocity is going to change, that means alpha. There's something I didn't write there that we oftentimes don't put down, but it's very important. It's the net torque, sigma t, tau, torque, right? So the back tire, the frictional force between the tire and the ground is not the only torque that is being produced. Where's the other torque coming from? You, right? You're pedaling the bike, and the chain is driving the wheel. If you were pushed, if someone came up behind you and pushed you on your bike, then both wheels would act like the front wheel, and the friction would be in the rear direction. But because you are pedaling, making the wheel turn this way, now it's trying to push backward on the ground, so the ground pushes forward on the bike, right? That's a Newton's action-reaction pair. Bike pushes on ground, ground pushes on bike, okay? So the important idea from all this discussion is the frictional force can be forward sometimes, can be backward sometimes, depends on the situation. What if the bike is already moving? You're not pedaling up to speed, but it's already moving, and you're just coasting at constant velocity. How much frictional force is present between the tires and the road, or which direction, I should say, is it now? Friction produces a torque, right? If you're moving at constant velocity, what's your alpha? 0. So what's your torque? 0. So what's your friction? 0. Okay, so while you're coasting on your bike, there is no frictional force between the bike and the road. It's only when you're changing speeds, when you have an acceleration. On page 279, there is an equation there in a little more than halfway down, 11-7. That is Newton's second law for linear motion. The sum of the forces is equal to mass times acceleration, and the sum of the forces in the x direction. So again, if we let the x-axis be the ramp, well, you see that frictional force is up the ramp, that's the positive x direction. The x component of the weight is pointing down the ramp, that's in the negative direction. So Fs minus mg sine theta is my sum of forces in the x direction, and that equals mass times acceleration in the x direction. And they're going to do an analysis by combining that equation with Newton's second law for rotational motion, equation 11.8 on page 279. R times Fs, we recognize Fs times R, that's the distance between the axis of rotation and the point where the force is being applied. So that's the torque. Torque equals I alpha. So ICOM is the moment of inertia about the center of mass, because we're treating this as rotating about its center of mass. And alpha is the angular acceleration. And then, we're not going to go through the yet, but turn the page on 280. They don't really show the analysis. I'm going to show it to you in a different way. But they come up with expressions for the frictional force and the acceleration of the center of mass. Now, the frictional force, let's not forget, it says Fs, but that is not necessarily Fs max. Okay? It depends on how steep the ramp is. The frictional force is going to vary. It's going to be some number between 0 and Fs max, and we don't know what it is. But with this equation, we can figure it out. Because remember, in the past, when we asked what is the frictional force of static friction, we always said mu times the normal force, but that mu coefficient always gave us the maximum frictional force, right? Now we have an expression that tells us the actual amount of static friction, not just the maximum amount, okay? And it's important to note that it could be less than Fs max, and most of the times it will be. When you get on your bike and you pedal really hard from rest, have you ever done it like on a gravel driveway? So hard that you actually, it's called peeling out. You know what peeling out is? It's when you pedal so hard that the frictional force cannot accelerate your bike fast enough, and you exceed the maximum static frictional force, and the wheel starts to slide. If you ever get on like a gravel driveway and put it in first gear, you know, the really easy gear to pedal, put it in first gear, get on the gravel driveway, and pedal right away as fast as you can, or as hard as you can, and you can get that wheel to slip and slide. That's called peeling out. Anyway, so that's when you would exceed the maximum static frictional force. But if that doesn't happen, let's say you just pedal slowly, just gradually gain speed, the frictional force is not as great as Fs max. Okay, so you get the idea. All right, so they come up with those two equations using one equation from linear motion and one equation from angular motion. And if you want to read it, you can do that later at your own leisure. I want to show you there is another way to do it. I could use two equations from angular motion instead of, and not even use the linear equation at all. So the first one I'm going to use is, just like the book uses, torque about the center of mass. And the book showed, and we talked about it, this frictional force times R is the torque produced by the friction, and it's rotating about the center of mass. What if we think about it as rolling about point P? Remember, we talked about that last week. You can think about this as rolling about its center of mass, so that it has rotational motion about its center of mass plus translational motion. Or you can think about it as purely rotational motion, where it's rotating about point P. And then the rotation takes into account the fact that it's moving down the ramp. Okay? So if I do that, now the frictional force acts through point P. So if I think about it as rolling about point P, does the frictional force produce a torque? The answer is no, because that force acts through the axis of rotation. Okay? So if I think about it as rolling about point P, though, now the weight does not pass through the point of contact or the axis of rotation, right? Now the weight has this small distance. In fact, I have it on the next slide. Here we go. I've zoomed in on this spot so you can see the weight is, here's my line of action. Remember, we talked about the line of action is that line that the force is on. And find the perpendicular distance from that line of action to the axis of rotation. So that's this little black line here. And if I look at this triangle, I see that the hypotenuse of that right triangle is the radius. And the angle of incline shows up in here. And this is the opposite side of that angle. So this side of the triangle is r sine theta. And so mg times r sine theta gives me the torque produced by the weight with this small moment arm right here. Or, an easier way of thinking of it, I think, is you just look at this. And we've already resolved Fg, the force of gravity, into its x and y components. The y component I didn't show here. But here's the x component, Fg sine theta, times r. Whoops, times r. So you can think of it as the component of force that's perpendicular, or you can think of all the force times the perpendicular distance. Remember, it's the same. Okay? So I come up with my second equation now. Torque about point P is r sine theta times the weight. And then I'll take a third equation that's acceleration is equal to r times alpha. We're relating the linear acceleration to the angular acceleration. But it's important to note, because of the way we've labeled our coordinate system, up the ramp is positive, and the wheel is accelerating linearly down the ramp. So it's accelerating in the negative direction, while the alpha, using the right-hand rule, is positive. Right? It's rolling counterclockwise, so that's positive. So I have to include that in my equation for acceleration. Negative acceleration is equal to r alpha. Okay? And you're used to seeing the tangential acceleration is r alpha. We recognize that the tangential acceleration for a smoothly rolling object is the same as the acceleration of the center of mass, and that is in the x direction. So these three are used interchangeably. So I'm going to use ax to mean the linear acceleration in the x direction. Okay? So those three equations now, I can use those three to come up with the equations that they show you in the book. They didn't show you the algebra. I'm going to show it to you. It's not a lot, as you can see. We're going to use Newton's second law of rotational motion, torque is equal to I alpha. And first we're going to look at it about the center of mass. So rearranging the equation, alpha is equal to torque over moment of inertia. And the torque is the frictional force times the radius. ICOM is ICOM. And that equals negative AX over R. And then I'm going to solve that equation for Fs. And this is what I come up with. Okay? And then I'm going to look at it about point P now. And now my alpha is torque over moment of inertia, both about point P. Torque we showed was right here, R sine theta times the force of gravity, the weight. And now IP, because it's about point P and not the center of mass, we have to use the parallel axis theorem. So the moment of inertia is ICOM plus mh squared, where h is the radius of the circle, of the disk. Okay? And again, just like before, it's equal to negative AX over R. And then I'm going to solve that for AX. Okay? And this is what I come up with right here, and this is the equation you see there in the book. And I don't want you to memorize those, okay? What I want you to get familiar with and understand fully is the process we took to get there, right? Understanding how the torque is produced, being able to identify the moment arm, and perform this process, not to just memorize these equations, okay? A couple things about this equation down here. We look at it, and let's take the example of the disk, okay? The moment of inertia of a solid disk like this is 1/2 mr squared. So if I plug that in for ICOM, the mr squares cross off, and this just becomes 1 plus a half, okay? So it's much simpler than it looks, okay? And if I use the hoop, the moment of inertia of a hoop, let's think about this. Which one of these has the greater moment of inertia? I see someone pointing this way. Well, in general, how do we determine how moment of inertia is affected by mass? What's the rule of thumb we've been talking about? If we change something about the mass, certainly the amount of mass, yes, but if we keep the same amount of mass in a given situation, keep the mass the same, can we change the moment of inertia with the same amount of mass? Yes. That's the key word I was looking for. The distribution of the mass. So I'm going to tell you, you have to take my word for it, these two disks have the same mass. But how is the distribution of the mass different? Here, all the mass is at radius r, isn't it? Here, some of the mass is at radius r, but a lot of the mass is at less than r, right? So what do we expect the moment of inertia of this guy to be compared to this one? Less, right? Remember, when mass is closer to the axis of rotation, that decreases the moment of inertia. And what does the word inertia mean? Well, it means resistance to changes in velocity, right? So what we can do is we can set up this little race between these two disks. Here's my starting gate. Okay, so we decided that we think the black hoop has a greater inertia than the brown disk. So if it has a greater inertia, when I let these go and they start to roll, a greater inertia means it will start to roll faster or start to roll slower? Slower, sure. So which one do we expect to get to the bottom first? Right. So the disk had a smaller moment of inertia and it got to the bottom of the ramp first. And when you look in table 10-2, you'll see that this is 1/2 mr squared, this is mr squared. So it's got twice the inertia that the disk has. And because ICOM is in the denominator, if it's a bigger number, it'll have less acceleration. And that's what we saw there, okay? How about if we took three objects that are they're listed as the same object in table 10-2. A sphere is 2/5 mr squared. So if we plug it in here, once again the mr squares cross off, and it would be 1 plus 2/5. or 7/5 in the denominator. This is a solid sphere of uniform density. This is a solid sphere of uniform density. This is a solid sphere. They're all solid spheres of uniform density. Are they really going to all have the same acceleration on this ramp?
Sure.
I don't know. What do you think? Let's set up our starting gate. Nathan, you don't want to miss this, man. Can everyone see? Okay.
Set.
The suspense is killing me. Go! Wow! Yes, they really do all reach the. They really do all reach the bottom at the same time. Amazing.
More or less.
Okay, so like I said, don't memorize these equations. We're just looking at how we got there, understanding torque, understanding moment arm, understanding parallel axis theorem, all that good stuff. Okay? And remember, the frictional force between the tire and the ground, between the wheel and the road, whatever, it can change depending on the situation. Okay, thank you. No homework.